All right, Physics 30s. We're going to tackle Chapter 16, at least the first part of it, on nuclear physics. And hopefully this will help you a little bit. There's some technical stuff here, but I'm confident you can wrap your head around it. So let's just start with a bit of the history here. We've kind of covered all of that in Chapter 15. One thing we didn't mention was nucleons, and that's Chadwick basically confirmed the existence of electrons. So what we have to start learning or using here is this word nucleons, okay? We're going to start calling anything that's in the nucleus of the atom a nucleon, okay? And that number will make sense when we start doing some balancing. So in summary, to this point, we've learned about electrons, protons, and neutrons make up the atom. The charge of electron and proton actually to 6 significant digits is listed here. Not that you'd ever need to know that. The mass is in kilograms. But we're going to start referencing a different kind of unit for mass, and it's called an atomic mass unit, or the symbol mu. Okay? Now, mu is the Greek letter mu, which is a U that's kind of got a tail in the front. You can see it better shown right here. And scientists, when they started studying the nucleus, quickly realized that dealing with kilograms was going to be a real pain in the neck, because it's so, these numbers here are just ridiculous, okay? Times 10 to the negative 31 and 27, and they're just small. So what they decided to do was take the mass of a carbon atom and cut it into 12, okay? A carbon atom would have 6 protons and 6 neutrons, okay, as well as 6 electrons. So they kind of chose that as their baseline, and basically chose one atomic mass unit to be equal to this 1.66 times, or basically 0.539 times 10 to the negative 27. On your formula sheet, which I should have had pulled up here for you, they basically just say that one atomic mass unit is equal to 1.66 times 10 to the negative 27 kilograms. That's what it says on your formula sheet, okay? So if you ever have to convert kilograms to atomic mass units, you can just use that. But know, though, that there's a high level of specificity here, because we're able to measure things with a fair degree of accuracy. And so we're gonna use atomic mass units in a lot of what I reference now. So, and that's what the appendix shows, and I'll pull that up in a second too. Okay. Now, when we're looking at the entire atom, this is a convention that you'll see, and you see it more in chemistry. We really don't use it much in physics, where you have the chemical symbol, and there's basically the atomic mass number is written up top, and then Z is called the atomic number, which is written right there. Okay, it's not going to hurt you to really see that, but I don't want you to stress about that too much. Because we tend to deal with the nucleus of the atom more, okay? Especially because we're dealing with nuclear physics. And so the convention, I'm going to leave that there, but just know it's not as important as what I'm about to show you. When we're actually writing the a nucleus of an atom, we tend to write it in this format right here, okay? A over Z as superscripts and subscripts, but right in front of the element symbol, okay? So I'm going to just show you a quick example, because they didn't really show one here in the notes. So I'm going to maybe tuck it in over here. A common element we'll talk a little bit about later is carbon 14. And if we write carbon 14, it's in one of the isotopes of carbon. It's really useful for determining how old something is. And you may have heard of carbon 14 dating. We're going to learn about that later. Carbon 14 can be written like this. You can write the element symbol, but carbon 14 has 14 nucleons in it. So we put that number up here as the superscript, and we put the proton number as the subscript that's leading it, okay? So there's 6 there's 6 protons in carbon. But if we look at the nucleons, okay, so that's the number of protons and neutrons. Carbon 14 actually has it has 2 extra neutrons. Okay, so it actually has 8 neutrons in its nucleus, and it has 6 protons. So 8 plus 6 is 14. Okay, so and that's really what this here is trying to emphasize, is that N in this, or sorry, not N, A in this case is the nucleon number. So when you're going to see a bunch of me writing a bunch of stuff here. This number up here is the nucleon number. Okay, so it's the total number of nucleons. And this number here is the proton number. Okay, now if you need to know the number of neutrons, like I already mentioned that math to you, it's really simple. All you have to do is just go 14 minus 6 and you get 8. Okay, so that 8, it would actually be the number of neutrons. Okay, so try not to confuse neutrons with nucleons. Okay, but anyway, it's just vocabulary. You guys will get it real quick. So this is a really important summary when it comes to dealing with atoms. And it's a great review of even chemistry too. But the first part is, if you change the number of electrons in an atom, you create ions. Okay, so by kicking out electrons or adding electrons, you're going to make ions. If you change the number of protons in an atom, you create elements. So if I change that 6 here from carbon 14, if I change that to a 7, it's not carbon anymore. Okay, that would push it to nitrogen. Okay, so if you change the proton number or the number of protons, you create elements. And if you change, so the last one then, if you change the number of neutrons in the atom, you create isotopes. Okay, and that's actually what carbon 14 is. There's actually carbon 13 and there's carbon 12. I think there's even carbon 11, which is really rare. But anyway, you can see that all these are all possible isotopes of carbon. Carbon 12 is by far the most plentiful, like 99% or something of the carbon you'd ever find just kicking around in the universe or even on our planet would be carbon 12. But there's a small percentage that can exist as carbon 13 or as carbon 14. Even. And but those isotopes usually aren't as stable as the main form, which in carbon's case is carbon 12. And we're going to look at stability because that's tied to radiation actually. So you should know these right here. Hydrogen, simplest atom on the periodic table, simplest element. It has 3 isotopes. The first one is just what we know as hydrogen, and we write it as 1,1H. The reason for that is because simplest hydrogen is just 1 proton and 1 electron, no neutrons. So that would make the nucleon number 1 and the proton number 1 because there's only 1 nucleon in the nucleus. Deuterium, though, has 1 proton and 1 neutron. So you add those 2 together and you get a 2 in the top, but you still have a 1 on the bottom because it's still hydrogen. We didn't change the proton number, we just changed the nucleon number. We added another neutron. And then the same thing, tritium. So tritium is like super heavy. In fact, you can make water out of all of these forms of hydrogen. You make water out of tritium, they call it heavy water or super heavy water or something like that. I don't know, it's kind of cool. But anyway, so yeah, hydrogen has 2 protons and 2 neutrons and 1 proton. And so it has a total nucleon number of 3, but it still has a proton number of just 1. Okay, so that pattern will carry forward. Now, So this brings up a really cool summary on forces, and these you just need to know. Okay, there's 4 natural forces in matter in our universe, and I listed them here in order of strength. Okay, so the strong nuclear force. This is the strongest force in the universe. It binds protons and neutrons together. And primarily, you have to realize, like, protons don't normally want to be together. They hate each other. The electromagnetic repulsion, in the first video, one of the videos I posted, did a great job of explaining this. the electromagnetic repulsion between two protons, okay, if, yeah, two protons, I've got two protons right here. Here's one and here's one. Okay, so protons normally hate each other. Like you can't get them together. They'll just repel because of the electrostatic repulsion. But if you can get them close enough to each other, and it's a really close distance, it's got to be less than 10 to the negative 15 meters. If you get closer than that, then another force binds them together. Okay, and that's called the strong nuclear force. That force is greater than the electromagnetic repulsion, and it holds the nucleus together. And yeah, there's nothing in the universe stronger than that. But the major limit, of course, is that it can only act over small distances. So in order for protons to fuse, which is what fusion is, if you remember that, and that's coming up, you need huge amounts of energy to get them to come close enough to each other that the strong nuclear force can take over, and then they're bound together. Okay, so anyway, the second strongest force is the electromagnetic force. This is the force that's trying to blow the nucleus apart. Okay, and it's always there. I just find that really fascinating. So as you add more and more elements or more and more protons together and get them to fuse, once you get a big enough atom or a big enough nucleus, I should say, it starts to become unstable. And that's why every element over, I think it's 83, which is bismuth. Okay, every element above 83 is not stable. Okay, and over long periods of time, for some of them it's thousands of years, but they will break apart, and that's what radiation is when elements break up and break apart, and that involves fusion and fission. But we'll look at that shortly. Okay, so anyway, the third force is the weak nuclear force. We won't do much at all with that, but it is involved in what's called beta decay, which we're going to study. It's primarily the forces that are acting on electrons, and also another weird particle called a neutrino. Okay, which is a really, really small particle. But gravity, gravity is the weakest link in the universe. However, it explains so much of what we know about what the universe is. So it is the weakest force, though. Okay, now here's where it starts to get a little technical. If you want to remove a nucleon from the nucleus, okay, we got my little nucleus here. If you want to remove something from the nucleus, that's going to take energy. Okay, and it has to be enough energy to overcome this strong nuclear force that's trying to hold it together. We call this energy binding energy, and it's a little misleading because it's really the nuclear force that's holding it together. But anyway, just bear with me here. So binding energy is defined as the amount of energy required to separate all the protons and the neutrons from the nucleus. Okay, so that's what the binding energy is. Okay, that's what we refer to as how much energy you would need to just like make everything go apart and be separate. But here's what's crazy. The binding energy can be determined on the basis of an unsettling truth. And here it is. The sum of all the masses of the individual parts of an atom is more than the mass of the complete atom. That means an atom actually has less mass than the sum of all of its separate parts. What does that mean? It's crazy. It's really crazy. Okay, so this is a little quick example for you. So I've got three. We'll call these the neutrons. Okay, so I've got three neutrons here, and we're going to bind them all together. And I've got three protons, and we'll bind them all together. Okay, and we'll say I have three electrons. Okay, so I have protons, neutrons, and electrons, and they're all stuck together in an atom. We'll say. Now, this mass is a certain amount. If you were to separate, though, all of the pieces, okay, so I'm just breaking them all up here. I've got three protons. I guess I'm doing lithium here. Three protons, three neutrons. Oh, just dropped an electron. And three electrons. So the point is, if you took all of those pieces, okay, see them all here in my hand, you took all those pieces separately, and you added those up, the total of all of the individual pieces would be more than the atom when it's all together. Okay? And it's not a huge amount, this mass, but we call this the mass defect. It's not a huge amount, but it's definitely not zero. And if you can figure out and anyways, as scientists started measuring all of the isotopes and atoms and everything, they realized that this was the case. Now, Albert Einstein had an explanation for it, which partially makes his famous formula that much more significant. Okay, but anyway, so we'll do this in a minute. But if you want to determine the binding energy, you first off have to calculate the mass defect, and then you use Einstein's equation to show what the binding energy actually is, because the binding energy is the energy equivalent of the mass defect. Okay, so this is where we're going to use Einstein's equation, E equals mc squared. Okay, and the energy equivalent, it can be in joules, or you can change it to electron volts. When you're using Einstein's equation, though, you have to use c as the speed of light, and the mass has to be in kilograms in order for this to work. Okay, so here's what I'm going to show you just quickly. Because we don't deal with kilograms, though, and I'm sure I showed you atomic mass units. Okay, so one atomic mass unit is equal to that really crazy number, 1.6. This was back in the notes. You don't really need to write it down. I'm just going to show you right here, 0.0539 kilograms. Okay, so one atomic mass unit is equal to that many kilograms. If we used the formula E equals mc squared, and we took this mass and we plugged it in there and multiplied it by the speed of light squared, we would get an energy in joules. Okay, now I'm not going to write that energy down, but actually it'll make more sense if I show it to you. So 6539 times the speed of light squared. Okay, so that's going to equal 1.4944 whatever to the 17th joules. Okay, now that's not a great number. I'm not going to use that for anything. So the trick is here, if we convert this into electron volts. Okay, so 1.6 e to the negative 19 joules in 1 electron volt. Okay, we convert it into electron volts, but then even in electron volts, it's a really big number. So then we convert electron volts into mega electron volts, okay, or million electron volts. And if we do that, then you get this number. Okay, I have it actually written down right here. One atomic mass unit, okay, this is mass, is equal to 931.494. Okay, for our purposes here, sorry, I'm drifting. For our purposes here, I'm fine if you just use 931.5 MeV. That is energy. Okay, so I'm just kind of getting you to trust me that an atomic mass unit, okay, which is this really ridiculously small number. Oh, I didn't even put an E there. That was to the negative 27, I think it was, kilograms. Anyway, that really, really small number in kilograms, if I convert that into energy using Einstein's equation and then convert that into mega electron volts, that is where I get this number from right here. Okay, and you'll see in the video that we use electron volts and mega electron volts to measure mass equivalence, or to definitely measure energy when we're dealing with nuclear physics. Okay, just using joules is so tedious. Like, as these monster negative numbers that are super hard to wrap your head around. Electron volts and mega electron volts, you can quickly draw comparisons, and it's a lot easier. Okay, so we're going to actually do this. We're going to calculate a mass, the amount of energy, or the binding energy, I should say, for an atom. Okay, so we're going to do that little thing I did with all the Legos. Now, so we can actually use, what we need to do is we need to find the mass defect. We have to get the difference in mass between, all of these pieces individually added together. Okay, the protons, the electrons, the neutrons. You have to add up all those individual masses, and then we have to compare that to the mass of the atom when it's whole. And they won't be the same. And we get that mass defect, and then we convert that into mega electron volts is the convention. Okay, so I'm just going to show you quickly this appendix now. This appendix has the masses of all the particles we'll need in atomic mass units. Okay, so up in the top right hand corner, here's the mass of the electron in atomic mass units, the mass of the proton, the mass of the neutron. Okay, and they all have 6 decimal places. It's really tedious stuff, but there's no way of getting around it. And then here we have the atomic mass units for a whole bunch of isotopes, okay, a lot of conventional ones. So if you need it, I'll make sure you have access to it, but I'm just showing you that you have access to a table that will help you figure this stuff out, okay? Now, this is the formula, and it's not on your formula sheet. This is the formula right here for determining the mass defect, okay? And it's connected with the it's connected with what we learned already from expressing an atom by writing its nucleus. Okay, we have Z and N here. Okay, so to find the big picture is we're going to try and find the binding energy, but to do that we have to find the mass defect first. Okay, so this formula delta M is the change in mass, or the mass defect. Okay, it's equal to Z. Z is the number of protons that's inside it. Okay, and we're going to multiply that by the mass of 11H. Okay, 11H is just hydrogen. Hydrogen has 1 proton and 1 electron. So if we want to get the mass of the individual pieces of an atom, we can basically, like if you have 10 protons, then in the, say it's neon, for example, you have 10 protons, you would just multiply 10 by the mass of a hydrogen atom, and that would take care of the protons and the electrons. Okay, so I know this is going to get a little messy here, but this here takes care of the protons and the electrons. Okay, separately. Then we're adding to that, N is the number of neutrons times the mass of a neutron. Okay, so all of this takes care of the neutrons, which is usually N with a 0. And then you have all those 3 pieces. Okay, and then all you have to do after that is subtract the mass of the actual atom, which will be less. And then you'll get a mass defect. Okay, so let's actually do this. What's really cool about all of this nuclear physics is that all atoms actually want to become like iron. Iron is the most stable element on the periodic table. And it's because it's kind of the sweet spot where the nuclear force and the electromagnetic force are perfectly balanced. Okay, so anyway, if we want to determine the binding energy per nucleon of iron, basically this would be iron 56 is what you would read here. Okay, so how do we do this? Let me just show you. The binding energy, the first thing we need to do is find the mass defect. So that's going to be Z times the mass of a hydrogen atom plus the number of neutrons times the mass of a neutron. All of that will be, and then we're going to subtract from that the mass of the atom. Okay, now bear with me because I'm going to jump around between this and our formula sheet. So for iron 56, the number of protons is 26. Okay, and there it is right there. That's the number of protons. We're going to multiply that by the mass of hydrogen. Okay, now you would have this sheet here. Hydrogen, I'm pulling it up. Hydrogen is this number right here, 1.007825. Okay, in atomic mass units. So 1.007825 mu. Okay, whoops. Okay, and I'm adding that as we talk here. Now, I guess we should come back so you can see this. So now we have to, there it is there. Sorry, I guess I should move this up just a bit. What we're looking at now is we need the number of neutrons. Okay, so 56 nucleons minus the 26 protons, that's going to equal 30. So it means in an iron, and this isotope of iron, there are 30 neutrons. Okay, and the mass of a neutron, I've already looked this up. The mass of a neutron is 1.008665 U. Okay, so I guess I was using square brackets prematurely. This here, if I add those two up, this first one takes care of the protons and the electrons. And my second calculation took care of the neutrons. So that in that way, I've accounted for the mass of all the individual parts of the atom. Now, all we have to do is subtract the mass of the atom. Okay, now this is iron 56. So let me pull this up here. Iron 56, let's find it. There it is right there. So iron 56, whoop, sorry. Did it too fast there. So iron 56 is 55.938. Oh, sorry. Yeah, it's 55.934938. Okay, so I'm going to add that over here. And again, I can't get around these small or all this many decimal places. So this is a fairly tedious calculation, but it's the best way to explain it to you. Okay, so come back to this. Okay, so I have, and that's in atomic mass units. Sorry, this is in atomic mass units as well. So if I do that calculation very carefully, there's a lot of entry here. When I do that, I get a mass defect in the end. It's going to be a small amount. It comes out to 0.528462 U. Okay, atomic mass units. Now, this is the mass defect. It's not the binding energy. But using what we just learned, Einstein's equation, if I can convert this energy into mass, then I have the binding energy. That's how much energy it would take to completely separate all of the protons and the neutrons in iron 56. This is how much energy it would take. Or sorry, this is the mass. I'm sorry, I'm getting ahead of myself here. This is the mass defect, not energy. Sorry. This is the mass defect. But the amount of energy that it would require is this converted into energy. And I'm just going to skip all those there's a bunch of steps because I have to convert this into kilograms and then times it by the speed of light squared. But I can do that really directly here by knowing that there's 931.5 mega electron volts of energy for every atomic mass unit. Okay, so all you got to do is multiply that by 931.5, and lo and behold, we get, let's see, 492.3 mega electron volts. That would be the binding energy. Okay. Now I got to brace you here. This is very technical stuff, but there's one more level of understanding, and that is we could take this amount of energy, and what they like to do is determine the binding energy per nucleon of the isotope. And some of you may have caught that up here. I didn't say anything about it, but now I'm coming back to it. Okay, it's per nucleon. So this here represents the total binding energy for the whole atom, but per nucleon, you just have to divide that by the number of nucleons, and that's 56. Okay, so if I do that, I get a total of, oh, here, let's just, you know what, I'm actually spilling right onto the next chart where you're going to see it anyway. So that's awesome. Per nucleon, it's going to be 8.79 mega electron volts per nucleon. Okay, per number of particles in the nucleus. And look at this. Here's the graph that shows this. This is, and if you make sense from the video, this is why everything wants to become like iron. Okay. And look, here it is. There's 8. So 8 point, we said, what did we say? 8.79. Should be pretty close. Yeah, 8.79. We kind of said that was what we got for iron 56. And that's pretty close to what it looks like it says here, because right in here, this would be, this looks like it would be 9, so 8, 9, and 10. And this is mega electron volts per nucleon, okay, is what's on the y-axis. And 56 is right there. Well, I can't really draw that too well. So it looks like it's maybe just a little bit above halfway or something. So yeah, that works. I think that confirms our calculation. There was about 8 point, ours was 8.79. It looks pretty close to this. This isn't, I can't blow this graph up too carefully for you. So, but this is it. Then this is what explains all the elements here. Look at this. If you're a small element like hydrogen or helium, guess what you want to do? You have a tendency, under the right conditions, to fuse into something bigger that's more stable, that has a higher binding energy per nucleon. So look at this. The atomic mass number is on the x-axis, but basically, if you're hydrogen or helium, you want, and look, there's oxygen, blah, 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 you just keep going. You want to make your way up towards iron. And this process is called fusion. Okay, this is where, you got protons and neutrons that are floating, or well, they're not floating around, but I guess they are technically. Under the right conditions, they will, if you can get them close enough together, then the strong nuclear force will bind them together. And that there's a greater probability of that happening because you want to become like iron. Now, if you're greater than iron, though, the electromagnetic force starts to become strong enough that it wants to blow you apart. Okay. And so look at this. The amount of the binding energy for elements past iron starts to go back down. See, look at this. It's starting to decrease the binding energy. Okay. So they're not as tightly held together, and they're not as stable. And look at that. There's basically lead and bismuth. See this, like here's tin SN50, but man, you get past lead and bismuth, and these elements along here, they are not stable on their own. They'll just separate. Okay. And uranium, there she is right there. Uranium was the primary element for the making of the first atomic bomb. And it's what's used in nuclear reactors too, because it's not stable. And under the right conditions, you can get it to break apart and release a whole bunch of energy. But this part here is fission. Okay. So on this side, everybody's trying to go back this way. And on this side, they're trying to go up this way. And everybody wants to be like iron. Okay. So, and actually that partially explains too why there's so much iron in the universe. Like the Earth is a magma core. It's made of molten iron, like lots and lots of it, like huge quantities. Well, anyway, I'm kind of digressing a bit, but the point is that the binding energy actually makes sense when you start looking at the principles of fission and fusion, which we're going to study a little later, not right away. Okay, so in light of that, I think I'm just going to pause this video and, actually, you know what? I'll give you one more here for number 1. Let's see. Yes. So if you're given, here, you're given the mass of the element, it's found to be that much in kilograms. What is it in atomic mass units? Okay, and then determine the element. So, yeah, this is so tedious. If you only used this from your formula sheet just for this one, you may not get it exactly, because I think I found it exactly when I used the whole version, which was 0.06 or 1.660539. I promise you won't see that on a test. I'm not going to make you do that. This is just getting a little finicky. So anyway, you just convert this into atomic mass units. And when you do that, you will get 235.043928 atomic mass units. Well, that's great, but what the heck is that? So this is where you would pull up your reference sheet here, and then you go looking for it. Okay. And look, I got 0.0235. So that's definitely uranium of some kind, but I got 2.35043928. Okay, this is 0.043930. So, you can see that the discrepancies here are a little annoying actually in some cases, but definitely this looks like we got U-235. Okay, uranium 235, not 238. 235 is like more unstable, but anyway, very interesting. So, I'll post the answers to the remaining questions on this one. And I think I will pause the video to just break it up because we do need to talk about radiation, but I'll save that for another video. Okay. So feel free to rewind this and go slow if you need.